All right, let's dive into one of the most mind-bending, absolutely wild ideas in all of science, quantum entanglement. I mean, this is a concept that truly baffled even Albert Einstein. But here's the thing, it sits at the very heart of how our universe actually works. So let's get into it and unravel this spooky connection together.
And to really get a feel for how big a deal this is, just look at this quote from Erwin Schrödinger. Yeah, the Schrödinger's cat guy, one of the founders of quantum theory. He didn't see entanglement as just some weird little quirk. No way. For him, it was the single defining feature that makes the quantum world so utterly different from the world we see every day.
So what is it exactly? Well, at its core, entanglement is what happens when two or more particles get linked up, basically sharing a single existence. From that moment forward, they act as a single unified system. What happens to one particle instantly, and I mean instantly, affects the other, even if they're on opposite sides of the galaxy. It's like they've given up their independence to become part of this inseparable cosmic duo.
Okay, to really wrap our heads around this spooky connection, we gotta see it in action. So let's start with a really classic, clean example. So picture this. You have a particle that has zero total spin. Think of spin as kind of like a tiny quantum version of a spinning top. Now, this particle decays and splits into two new particles. Because of the laws of physics, conservation laws, their total spin together still has to be zero. So what does that mean? It means if you measure one of those particles and find its spin is up, you know right then with 100% certainty that its partner, wherever it is, has a spin that's down. That perfect instantaneous correlation, that's the telltale sign of entanglement.
And this instantaneous link, this is what just drove Albert Einstein crazy. He could not get on board with the idea that measuring a particle right here could instantly influence another particle way, way over there. It seemed to break the universe's ultimate speed limit, the speed of light. He famously and pretty dismissively called it spooky action at a distance.
Now, Einstein, along with his colleagues Podolsky and Rosen, didn't just complain about the idea. Nope. They came up with a really powerful logical argument against it, which we now know as the EPR paradox. Okay, so this slide just nails the heart of the conflict. It was a clash of two totally different worldviews. On one side, you have the quantum view, which says the particles are in a fuzzy, undecided state right up until you measure one. The act of measuring one instantly solidifies the state of its partner. But on the other side, you have Einstein's view, which we call local realism. It's built on two ideas that just feel like common sense, right? Locality, that nothing can travel faster than light, and realism, that objects have real, definite properties even when we aren't looking. So Einstein argued there had to be hidden variables, like a secret instruction manual, that determined the spin of each particle from the moment they were created.
And the physicist John Bell came up with a brilliant way to explain this hidden variable idea. He had this colleague, Dr. Bertelsmann, who, for whatever reason, always wore mismatched socks. So if you looked and saw he had a pink sock on one foot, you knew instantly, with no spooky action required, that his other sock wasn't pink. Why? Because the information was already there. The decision was made when he got dressed that morning. That's how Einstein thought entanglement had to work. No spookiness, just us not having all the information yet.
For decades, this was basically a philosophical debate, quantum weirdness versus classical common sense. But then, that same guy, John Bell, he figured out a way to take this argument out of the philosophy department and put it into the lab. So, in 1964, Bell did something absolutely ingenious. He came up with a mathematical test. He proved that if Einstein's hidden variables were real, if the universe worked like Bertelsmann's socks, then there was a hard limit, a ceiling, on how strongly the measurements of those two particles could be correlated. That limit is what we call Bell's inequality. The experiment itself is actually pretty straightforward in concept. Here's the game plan. You make thousands, millions of these entangled pairs. Then you measure their spin at different, totally random angles. And finally, you just count up the correlations. So this set up a clear ultimate showdown. If Einstein and local realism were right, the results would always stay under Bell's limit. But if quantum mechanics was right, the correlations would be so strong they would blow right past that limit, violating the inequality. So the stage was set for one of the most important experimental showdowns in the history of science. What did they find? What was the verdict?
Well, this timeline tells the whole story. It started back in the 70s with Friedman and Clauser, then it continued with more and more precise experiments from people like Alain Aspect. And every single time, with more precision, closing every possible loophole you could think of, the answer was always the same. Reality does not play by Einstein's common sense rules. The quantum correlations were way stronger than local realism could ever allow. Bell's inequality was violated over and over and over again. And this work was so incredibly fundamental that it earned the 2022 Nobel Prize in Physics.
So, the conclusion is just inescapable. Einstein's comfortable, common-sense view of the universe, where things have definite properties and nothing travels faster than light, well, that's just not how reality works. It's wrong.
And what does that mean? It means the universe is in fact spooky. That non-local connection that Einstein hated so much is a real, fundamental feature of our reality. The world is just so much stranger and so much more interconnected than our brains are built to handle.
But hey, this discovery isn't just a philosophical party trick. Understanding and actually using this spooky connection has moved out of the lab and into the real world, and it's driving some of the most revolutionary technologies we can imagine. I mean, seriously. Entanglement is the fuel for the whole quantum revolution. It's the magic ingredient in quantum computing, which will give us processing power that dwarfs today's supercomputers. It's the bedrock of quantum cryptography, creating communication channels that are literally unhackable by the laws of physics. It even makes quantum teleportation a real thing. Not for people, of course, but for transferring pure information, a fragile quantum state, instantly across space. This stuff isn't sci-fi anymore. It's the future being built as we speak. And that brings us to the final thought here. The discovery of entanglement basically ripped up our most basic assumptions about reality, about space and time itself. It proved that the universe is connected in these deep, mysterious ways we're only just starting to understand. So it really forces you to ask the question, if reality is this weird at its very foundation, what other profound, spooky secrets are still out there, just waiting for us to find them?